Hello. In this video, I want to take the derivative of a curve that we haven't looked at before, but it's still one that we're somewhat familiar with. This is the curve y is equal to the arcsine of x. So this is basically, it's kind of hard to say I'm going to say the inverse trig function. The whole inverse notation thing gets kind of mixed up. That's why I used arc here instead of the negative first power or whatever. But we have this function y is equal to the arcsine of x, or it's the angle that corresponds to a sine ratio of x. Now then, what is this going to look like? Well, it's going to look a little bit like this. This is not perfect. This is just my interpretation. This is the curve y is equal to arcsine of x. All right then. So how do we take the derivative of such a curve? Well, this is obviously not a function as defined formally because look, vertical line test, this does not pass it. Look at all these points of intersection here. So it's obviously not a function. So maybe we'll use a little something called implicit, we've done this a million times now, implicit differentiation. Yay. Implicit differentiation. So we're just going to take the derivative of both sides of this equation. But wait a minute. We can't do that because what's the derivative of this? I have no idea. That's such a strange expression there. It's kind of, you don't just look at that and say, oh, I know the derivative of that. So what we're going to do is we're going to change this into the formula sine y is equal to x. And now we do know kind of how to work with the derivatives of both functions on those sides. So what we're going to do first is we're going to take the derivative of both sides. Go back to my orange. We're going to have that the derivative with respect to x of sine y is equal to the derivative with respect to x of x. So we have, what's the derivative with respect to x of x? That's just 1 is equal to, okay, the derivative with respect to x of sine of y. So we're going to treat y kind of like a function of x. We're going to use the chain rule. So what's our outer kind of function or expression, as I like to say just to avoid some confusion? We have sine x on the outside, and we have y on the inside. So all we do is we take the derivative of the outer function, sine x, except we plug in y for x when we get the derivative, and then we multiply that by the derivative of y. So what's the derivative of sine x? Well, that's cosine x, except we have to say cosine y because we plug y in for what we would normally treat as x. Then we multiply by the derivative of the inside, which I'm just going to say is dy dx, because we haven't defined y any other way than what's up here. And we're looking for dy dx. This is what we're trying to find after all. What is the derivative in terms of y with respect to x? And in this case, we're going to get an answer in terms of x and y. Well, sort of. We're going to get one with respect to y first, and then we're going to get one that involves x. So not x and y, but we'll get to that. So we have that dy dx times cosine of y is equal to 1. So obviously dy dx is equal to 1 over the cosine of y. And you could say, all right, I'm done. If we just take any point on here, we know the y value, we can find the slope, and that's going to be the slope of this line is going to be equal to the cosine of this y value, cosine of y. I'm sorry, 1 over that value. 1 over the cosine of y. However, there is one more thing we can do here to get a slightly different answer, only in terms of x. Now obviously, at any point x, just if we look at this graph here, at any one point x, if I choose this point, look at all these different points, and they all have different slopes. So we have to add a parameter where this is defined as a function. And that's going to be, well, what if we just walled this area off here. If we just looked at what's between, if we just look inside this box, if we change the range of this graph so that we're only looking at this little blue part in between, and I'll even color that, let's see, let's color it red. If we're only looking at this part of the curve, and it's just kind of interesting to see what the derivative of this part of the curve is with respect to only x, just because you can get it in terms of x, but it obviously doesn't mirror the whole function, and while maybe it's not the most useful thing, and you might be a little bit confused about, okay, why do we care about this tiny box? It's more to do with how this might appear in textbooks, and I'd like to at least explain why that's the case. Usually you look at this, I mean, it does tell you something about how the function is changing, right? At least in that interval. So let's find that. Well, what is that interval going to be? We're going from, I mean, and here you really just need to think about the normal graph, and I think I'm gonna graph this again down here. Let's just carry our graph down a little bit. Let's make another one down here. Yeah. So our graph right now looks like this. And if you think back to a normal, here's y and here's x. If you look back at what a normal function where we had, say, that instead of sine y is equal to x, y is equal to sine x, you know, that looks a little bit different. We have more like this. So, and I hope this helps visualize what we're looking at here. This y value is going to be pi over 2, right? Because pi over the sine of pi over 2, sine of y, that's going to be 1. That's going to be the highest point. So that's going to be the highest x value, and that's clearly what we have here. And then the lowest point is going to be sine of negative pi over 2. So that's the interval we're dealing with. And I'm going to quickly erase that other graph I made because I don't think that's necessary anymore. So now if we go back to taking the derivative, I'm just going to make a parameter. I'm just going to say, okay, so now, maybe I'll even change colors of this. I'll change to purple. Yeah, let's do that. So now I'm going to say, so if we're taking y, let's do this over. Y is greater than negative pi over 2 and is greater than, I'm sorry, it's less than, yeah, I screwed this up. So I was getting so ahead of myself. We have that y is greater than or equal to negative pi over 2 and is less than or equal to pi over 2. I'm not sure why I didn't write that down right the first time, but that's the range we're dealing with, right? That's between here and here. That's the part that we're looking at. Then this becomes a function. And what is y equal to? Well, not this. Y is equal to the arcsin of x. So let's just plug that in. Let's just plug that in. We're going to say that dy dx is equal to 1 over the cosine of the arcsin of x. And now we're going to have to make a triangle, obviously, to look at this, because it's kind of, it's kind of hard to know off the top of your head, well, what's the cosine of the arcsine of something? But we can draw that if we have some right triangle here, and the angle that we're taking the cosine of, arcsine of x, some angle here, and its sine is x. So that means that the opposite over the hypotenuse will be equal to x. So we can just say that the opposite side is x and the hypotenuse is 1. Why not? That fulfills the conditions. So then what's the cosine? Well, we need to know the adjacent side. So by the Pythagorean theorem, this is going to be the square root of 1 minus x squared. Therefore, the cosine is this over 1. The cosine is just this value here. We're going to have that dy dx is equal to 1 over the square root of 1 minus x squared, given this. So this is what leads to this answer. So if we look at this range, if we look at this interval here, we can say that at any point, the derivative of y, now it's a function, the derivative of the function that maps to y with respect to x is 1 over the square root of 1 minus x squared. In the next few videos, we're going to be doing this for cosine and tangent. I hope this video wasn't too long, and thanks for watching.